Their brains are not the same. A week ago, the Artemis II crew splashed down off the coast of San Diego. A day later, 4 astronauts walk onto a stage in Houston to wave at cameras, hug their families, and smile for photographs. What nobody outside a small circle of NASA flight surgeons wants to say out loud is that the organs sitting inside their skulls physically moved while they were gone, and some of what changed may not change back. For almost a decade, peer-reviewed studies of astronaut neuroimaging have been reporting this quietly in journals most people have never heard of, while the press conferences stick to flags, music, and triumphant speeches. No human brain has ever traveled as far from Earth as the 4 that came back from Artemis II, and no human brain was ever designed to make that trip. Your brain is not glued to the inside of your head. It floats. It sits suspended in a layer of cerebrospinal fluid, a clear, salty liquid that cushions it, feeds it, and flushes it clean. On Earth, gravity pulls everything downward. Blood pools in your legs. Your heart spends its entire life pumping uphill to your skull. Your body has spent billions of years evolving for exactly this arrangement. Now take that arrangement and remove it. The moment the rocket cleared the tower and the crew transitioned into microgravity, the rules changed. No more down. No more pooling. Fluids that normally sat in the lower half of the body began migrating upward toward the chest, toward the neck, toward the head. Astronauts call this puffy face chicken legs. The face swells, the legs thin out. And anyone who has seen photos from space has seen this without realizing what they were looking at. What they weren't seeing is what happens above the jawline, because that fluid shift does not stop at the cheeks. It keeps going. It pushes upward into the skull, where there is nowhere for it to go, and it starts rearranging things. Within hours of reaching orbit, the brain begins to drift upward inside the cranium. Over longer missions, scans have shown the brain physically displaced toward the top of the skull, pressing against bone, narrowing the spaces where cerebrospinal fluid is supposed to flow freely. Studies have documented measurable structural changes in astronauts who spend extended time in microgravity, especially those on missions lasting 6 months or more. Artemis II lasted only 10 days. That's the obvious counterpoint. But here's the problem. We don't actually know what 10 days beyond low Earth orbit does to the human brain. Only 24 people in history have ever traveled that far, and the last of them came back in 1972, before modern brain imaging even existed. That means the Artemis II crew are the first humans ever whose brains have been scanned before and after a journey beyond the moon. Whatever those scans show, we've never seen it before. Inside the brain are fluid-filled chambers called ventricles. In astronauts, these have been shown to expand in microgravity. The changes sound small, fractions of a milliliter, but the brain is sensitive to even tiny shifts in structure. What's more striking is how long recovery takes. In some cases, it can take years for these structures to return to something resembling normal. For a short mission, the effects should be smaller. But should is not the same as are. Then there is radiation. Astronauts in low Earth orbit are still partially protected by Earth's magnetic field. The Artemis II crew were not. Once they passed beyond that shield, they were exposed to the full radiation environment of deep space for the first time in more than half a century. Galactic cosmic rays, solar particles, high-energy protons, heavy ions. These are not abstract hazards. They pass directly through the human body, including the brain, leaving microscopic tracks of damage behind them. A single high-energy particle can disrupt cellular structures or damage DNA. In animal studies, this kind of exposure has been linked to measurable changes in learning, memory, and mood. The human brain contains around 86 billion neurons. During those 10 days in deep space, a small but real percentage of them were directly hit by radiation. Nobody knows exactly what that means yet. Now imagine this. You are sitting at home, and every few seconds, a cosmic ray passes harmlessly through your body. You don't feel it. You never will. In deep space, that rate increases dramatically. Hundreds of invisible particles pass through you every day, threading through tissue, including the delicate structure of your brain. That was the background environment inside the spacecraft. Then there is pressure. On Earth, fluid pressure inside the skull is regulated in part by gravity. Stand up and fluid redistributes. In microgravity, that mechanism disappears. Fluid accumulates in the upper body, and pressure remains slightly elevated for extended periods. Over time, this begins to affect the eyes. A significant percentage of astronauts on long missions develop a condition that alters the shape of the eye itself. The back of the eyeball can flatten. The optic nerve can swell. The retina can develop folds. Some astronauts return with permanent changes in vision. Some need glasses they never needed before. In a few cases, structural changes persist for years. For a 10-day mission, the risk is lower, but the same underlying forces were present from the moment the crew entered microgravity. The brain adapts quickly to space. Without gravity, the inner ear no longer provides reliable information about orientation. So the brain starts ignoring those signals and relies more heavily on vision and body awareness. This works in orbit. But when astronauts return to Earth, it becomes a problem. The moment gravity comes back, the inner ear starts sending strong signals again. The eyes say something different. The body struggles to reconcile the mismatch. The result is disorientation. Balance becomes difficult. Movements feel uncertain. Even standing upright can be a challenge in the first hours after landing. Astronauts often describe another effect as well. Space fog, slower thinking, reduced concentration, words that don't come as quickly, subtle but noticeable cognitive changes. Studies of astronauts returning from longer missions have documented these effects lasting for weeks or even months. The brain, it turns out, takes longer to readjust than the body. Imaging studies have shown that spaceflight can alter both gray matter and white matter in the brain. Some regions increase in volume, others decrease. The connections between different regions shift, especially those involved in movement, balance, and spatial awareness. Some of these changes are likely adaptive, helping the brain function in an environment it was never designed for. But when the astronaut returns to Earth, those adaptations have to be undone, and not all of them reverse cleanly. There are even more subtle effects. The brain has a system that clears waste products during sleep, relying on the movement of fluid through microscopic channels. Evidence suggests that these pathways may change in space and remain altered after return. Scientists are still trying to understand what that means for long-term brain health. None of this means the Artemis II crew is in danger. None of this means the mission was reckless. And none of this diminishes what they accomplished. They traveled farther than any humans have gone in more than 50 years. They carried the weight of history, of expectation, of personal sacrifice. They came home to applause for a reason, but it does mean something else. It means this kind of travel is not routine. Every time a human leaves Earth's magnetic field, they enter an environment that pushes the limits of human biology. Every time fluid shifts into the skull, something changes. Every time radiation passes through the brain, there is a chance small but real, that something is altered at the cellular level. NASA does not emphasize this in public celebrations, not because it is hidden, but because it is complex, technical, and not easily reduced to a headline. Welcome home is a cleaner message than your brain may still be adapting, but the story does not end with the splashdown. Over the coming months and years, the Artemis II crew will undergo repeated scans, tests, and evaluations. Their brains, their eyes, their balance systems, all will be studied in detail. The data will feed directly into future missions, including plans to send humans back to the moon and eventually to Mars. And Mars changes everything. A mission there would take years, not days. Most of that time would be spent in deep space, exposed to radiation and microgravity far longer than anything experienced on Artemis II. The effects we are only beginning to measure would have time to accumulate. There is no quick return. From Mars, no early exit if something goes wrong. The crew would have to live with whatever changes occur until the mission is complete. That is the future these missions are building toward. So when you watch footage of astronauts smiling on a stage, it is easy to think the story is finished, that the mission ended the moment the capsule hit the water. It didn't. The real mission is still unfolding, quietly, slowly, inside their bodies, inside their brains, somewhere between the scans taken before they left and the scans taken after they returned. Something changed, not dramatically, not visibly, but measurably. They went farther than almost anyone ever has. They came back. But part of what they experienced came back with them, embedded not in memory alone, but in the physical structure of their own minds. And it may take years before we fully understand what that means.